Hello. In this video, I want to introduce PQSecure-Boot, our quantum-safe secure boot solution. Secure boot is the foundation of trust on every modern device, but current implementations rely on cryptographic primitives that are threatened by quantum computing. PQSecure-Boot is designed to address this threat by providing quantum-safe secure boot. In this presentation, we'll discuss three topics. First, what secure boot is and why it matters. Second, what post-quantum cryptography, or PQC, is, and why its adoption has become so urgent. And finally, how PQSecure-Boot combines these elements into a single quantum-safe secure boot solution. We'll begin with Secure Boot itself. The core problem addressed by Secure Boot is trust. When a device powers on, how can we know that the software running on it has not been tampered with? If an attacker had replaced firmware during some stage of the supply chain, how would we detect that? Because mutable storage cannot be trusted, we must anchor the trust in something immutable. This diagram illustrates the resulting chain of trust. It begins with a piece of immutable firmware paired with an immutable public key, both stored in one-time programmable memory at manufacturing time. In step one, that trusted firmware uses the OTP public key to verify the bootloader signature. Once verified, the bootloader itself now becomes trusted. In step two, the bootloader uses its own embedded public key to verify and load the application code, such as the operating system or bare metal software. Then, the authenticated application can in turn validate any additional modules it requires. Each link extends the trust from the previous one. If any signature check fails, the device detects the error and refuses to boot. To give a bit more detail, this diagram shows the different elements that are used in Secure Boot. Signing is performed offline by a hardware security module that holds the cryptographic private keys. In this case, a hybrid signature is being used composed of a classical ECDSA key and the post-quantum MODSA key. These corresponding keys are used to create the manifest, which consists of the program images with the corresponding public keys, an image hash, and the signatures. The signed code is what is ultimately programmed into the mutable flash memory. On the device itself, only one piece of data must be immutable, the hash of the public keys, which are stored in the OTP fuses. At boot, the ROM performs three checks. First, it reads the public keys from the manifest and confirms that their hash matches the expected fused value. This establishes that the keys themselves are trusted. Second, it verifies the signed image hashes against the public keys and signatures. Then it hashes the code and verifies that that hash result matches the hash result stored in memory. If all of these checks pass, then it has been cryptographically proven the code has not been modified and is from the expected source, and so the boot process can continue. It is critically important for the secure boot operations to be performed in specialized hardware. The security of the system is ultimately rooted in the immutable keys stored in the fuses and in the hardware integrity of the software ROM that's used to perform the initial verification. With specialized hardware, that ROM that orchestrates the boot flow can be kept deliberately small, which both minimizes the code-based attack surface and allows for careful security analysis of the code. Additionally, the security policies, such as anti-rollback for software versions and key revocation, can be enforced in the hardware. This is accomplished by irreversibly burning OTP fuses rather than by using a software policy which could be potentially modified. Now, in our example so far, we've showed hybrid signatures using both classical and post-quantum algorithms. But in reality, every signature check in that chain today relies solely on either ECC or RSA, both of which are broken by Shor's algorithm running on a sufficiently large quantum computer. And recent estimates from academic research place the arrival of these quantum computers somewhere between 2027 and 2023, which is well within the lifetime of products being designed today. Fortunately, the necessary solution is already available. NIST has already standardized a family of post-quantum primitives, primarily MOChem and MODSA, which are the main recommendations under CNSA 2.0, which are also complemented by the stateful hash-based algorithms XMSS and LMS, which are permitted for firmware updates. These algorithms are quantum safe, but are still executed using classical hardware. So it's critically important for all new systems to be deployed with these new post-quantum algorithms in order to maintain security into the future. However, even with the correct algorithm selection and implementation, there are still attack vectors which can break a secure boot implementation. The signature check may correctly reject a malicious firmware image, but the final decision still depends on hardware enforcing that result. An attacker can target this enforcement point using voltage glitches, clock glitches, or electromagnetic pulses. A well-timed fault can skip a branch or corrupt a status flag, causing a rejected malicious image to still boot. Similar attacks can also bypass anti-rollback checks to revert to an older, vulnerable firmware image. Countermeasures for this include things like redundant checks, hardened control flows, protected verification flags, and locking out debug and test interfaces. But fault injection resistance must be considered very early in the process, since vulnerable points are often hidden in the control logic, state machines, and the verification flags themselves. Once the hardware architecture is fixed, these weaknesses can become very difficult to track and eliminate. Our product, PQSecure-Boot, brings these principles together into a single product. At its core is a dedicated RISC-V security processor embedded in silicon alongside the ROM, OTP fuses, and cryptographic accelerators. The ROM software code is optimized to minimize the code size, while the hardware cryptographic accelerators are optimized to minimize the silicon footprint. Both post-quantum and classical accelerators are available. This includes MODSA, SLHDSA, and LMS for quantum security, ECDSA and RSA for classical security, and of course SHA-2 and SHA-3 for image hashing. Depending on the specific application needs, the algorithms can be optionally removed from the design to save silicon area. And of course, the ROM software in each of the cryptographic engines includes robust fault injection countermeasures. PQSecure-Boot provides all of the following: firmware authentication established through dual signatures from the silicon vendor and the device owner, quantum resistance provided by MODSA, SLHDSA, and LMS, all of which have implementations that have been validated under the NIST CAVP program. Hybrid security during the classical to PQC transition can be maintained through parallel usage of ECDSA and RSA. Anti-rollback is enforced by a one-time OTP version number ratchet, and key revocation by a permanent per-key OTP bit mask. Binary integrity is established by SHA-3 or SHA-2 hashing of a very firmware image, and the ROM itself is protected against fault injection by control flow integrity countermeasures. Together, these properties provide defense in depth from algorithm selection down to silicon implementation. Solutions are available for any system, including standalone hardware configurations targeting new manufacturing runs of FPGAs, ASICs, SoCs, and chiplets, as well as software retrofits for existing devices. Thank you for your time and attention. If you have any questions about PQ Secure Boot or any of our other cryptographic solutions, please contact us through our website.